Okay, so some quick reminders, announcements as we're getting rolling. So our first exam is coming up pretty soon. So if you haven't been studying, start. But on that note, I like to put up a full-length practice exam for you guys to work with. So expect to see that coming up possibly tomorrow, and I'll talk to you on Friday about how to use that and how I design that, but it should give you a good sense of like, not the exact questions that will be on the exam, but in terms of format, kind of wording, and even a little bit distribution of topics should be somewhat similar. So if you're thinking about ways to study, that's one possible avenue. Cool. All right, that said, we are gonna be covering content today. We're gonna jump back in. So when we last talked, we've been talking about passive transport. We're in general talking about types of transport. So we have been looking at what it looks like when something crosses our cell membrane down a gradient in the favorable direction, and different ways it can do that and what that means for speed. Okay, so we had talked about simple diffusion and how we can have something that just diffuse directly across the lipid bilayer. So those are going to be things that are non-polar, hydrophobic in general. So they're going to be going really just down a concentration gradient because our electrochemical driving forces are really kind of specific to ion. And we talked about facilitated diffusion, so molecules that can't get directly through our phospholipid bilayer because they are polar, maybe they have charges, but they can, or they're just big, but they can use a protein to get carried across using a carrier protein across the membrane. And we had talked about diffusion channels that basically act as pores in the cell membrane, allowing things like ions to get through. We had spent a little bit of time thinking about rates of transport as well. So we talked about how a bigger gradient, a bigger force, pulling something into the cell or pushing it out is going to, in general, speed up the rates of transport. So concentration gradients are kind of driving force, has an effect on how fast transport happens. But in our example, the passive transport that includes one of our integral membrane proteins, a transmembrane protein. So when we need a protein for help, we're also going to have to pay attention to, okay, how fast does that protein actually work? Like how fast does it, for example, carry something across the membrane? How fast does it flip? And we're also going to have to think about how many of that protein do we have in our membrane. So those aren't all the things that we were paying attention to, but those are some of our like kind of headline items for things when we're thinking about rates. So today we're going to be talking about active transport. So everything we talked about last time, happening without an input of energy, so long as we have the right carrier protein, as long as we have an open channel, this is good. Our passive transport, everything we talked about last time, just going to happen automatically. With active transport, we're going to be thinking about things that are moving in a direction they'd rather not go. So we're going to be using some source of energy to power this movement when we're thinking about active transport. Okay. So active transport isn't going to happen spontaneously. So we're going to have to input energy, we're going to have to pull, we're going to have to push with some type of energy. And at some point in our process, we're usually going to see some type of pump involved, right? So when we talk about a pump is going to be a specific type of membrane protein. It's going to be a transport or something. Usually we're talking about our sodium potassium pump when we're thinking about pumps, but that's not the only one that exists. We'll talk about the sodium potassium pump in detail in a little bit. Okay. But basically, anytime we are moving away from a sort of equilibrium state, right? So
everything's fine. We have no net flux. We're at equilibrium if we have equal distribution of our particle, our molecule on either side, right? No net movement. But if we input energy through active transport, we can push things to a point where we do see a difference in that distribution, right? And we can maintain concentration gradients like this using a pump. We're going to identify active transport more generally anytime we see something moving on the whole if it's in equilibrium, but usually our examples are going to be when we see things going from low to high concentration. So that's not a completely in every situation in the world. Is that true? But this is what we're really looking for our purposes, because that's mostly what we're observing when we're looking at active transport. So we think of this as uphill movement, and just like you need to put in energy to roll a boulder up a hill, you need to put in energy to do active transport. The energy is usually coming from that pump at some point in the process. Okay. So we can see that a pump, and in this case, we are zooming in now on our sodium-potassium pump, which is our pump that we're going to see over and over and over and over and over again in physiology and in this course. Right, so we can see it's a transmembrane protein going all the way across the membrane. It's an integral protein. It's integrated into the membrane. And we can see that it is doing a couple different things here. So one thing that it's going to do is it's going to act as a transporter. So just like our carrier proteins in facilitated diffusion, we can see that we have these binding sites. The ones we're looking at the moment on the slide are for sodium. So we can see these binding sites for sodium. And we can probably predict that we're going to have a shape change here with the sodium binds in, and we're going to have some movement. In this case, we're going to ultimately be taking sodium out of the cell. So these free sodium that are found in right here at the moment are going to end up ultimately in the extracellular fluid. And the way we power this with our sodium potassium pump is that they also have a part that acts as an enzyme, right? So down here, you can see that we're taking ATP, which is where we're storing all our cellular energy, right? We did cellular respiration, we got our energy out of glucose, stored it in the form of ATP. Now we're using it, okay? So we take ATP with its 3 phosphate groups, and we break it down, leaving us with our lower energy molecule, ADP, with only 2 phosphate groups, and the phosphate group that we pulled off here. Okay, so this is its sort of enzymatic function here is breaking down ATP. Yeah. And that's going to allow us to harness the energy that was in that final bond of the ATP to move our sodium, in this case, in a direction the sodium don't necessarily want to go. They don't want to go. Okay. So things that we can notice about this, we've got these specific binding sites. Because we have specific binding sites, in this case, we've got 3 binding sites for sodium, these proteins can get saturated. When we say saturated, we mean full, right? So once these binding sites are full, you're not going to see more sodium binding in. There's nowhere for it to go. So we would describe that as being saturated. Okay. Now, we're usually going to see a pump involved at some point in active transport, but what point is going to differ between our 2 types. In primary active transport, we're going to see the ATP used pretty directly. So you're going to see something like that pump. You're going to see ATP being broken down, right? So that's what we think of as the first step, kind of. So it's primary because it comes first. But with primary active transport, we can set up and maintain gradients, right? So you imagine that sodium potassium pump working, shoving sodium out of the cell, shoving sodium out of the cell over and over and over again. We set up a gradient where we have lots of sodium outside the cell and only a little bit inside. In secondary active transport, that's like the second step. So in secondary active transport, instead of directly seeing that we're using ATP, we're going to be using that gradient that we set up by primary active transport to carry something along with our molecule that's now getting released and traveling in the direction it wants to go. Okay. So here we're looking again at that sodium potassium pump because we weren't quite done, but it's a great example of primary active transport where we directly see this use of ATP, right? So we can see that ATP being broken down at that enzyme part of this pump, at that enzyme part of this protein, right? So this happens to also be describable as a hydrolysis reaction. So usually there would be water in the byproduct here as well. Okay. So here you see what happens after we have that ATP bind in. Right now we have these sodium out in the extracellular fluid. We're going to see that when we focus in on a sodium potassium pump, we're not actually done yet. Right? The sodium potassium pump, because to reset, we're going to be pulling potassium back into the cell. But for our purposes, right, when we're just trying to identify that we have primary active transport happening, we're looking for, is it some type of a pump? Which means, do we see some energy use? And if we saw gradients or forces on here, right, we might think about sodium gradients. We might see low to high, or maybe, no, that is what I mean, right? So passive would be going from high to low. In this case, we're going from low sodium concentration to high sodium concentration. So we're packing it in there. So that might be a hint that this is going to be active transport, primary active transport. Now that we know about our electrochemical driving forces, right? We know from an example we did in class before, we could do it out again, that our electrochemical driving force for sodium points in, right? So we know that we have a force that's trying to push sodium into the cell, right? So by kind of examining that situation, right? And when we see sodium continuing to go out of the cell, even though we know it wants to come in, right? So when we see sodium traveling out, right, we know that's going against this force that's pushing it in. So we must be pushing really hard, continue to shove it in this direction. So when you assess these, you want to be looking for like the baseline state of like, where does this molecule want to go? If it is going in the direction it wants to go, you've got passive transport. If it's going in a direction it doesn't seem like it should be going, you've got some type of active transport. If this is happening using energy directly, it's primary active transport. Our secondary active transport is what we might do with a gradient that we've already set up through some type of primary active transport. So it's like our second step. I do personally like kind of shorthand it as a second molecule. You'll see a second molecule or a second particle or substance usually involved in secondary active transport because of this. So a thing to notice about diagrams in your book is that they use green when it's in a good direction, a passive direction, a spontaneous direction, a favorable direction. You could describe it any of those ways, right? And they use red when it's going against its gradient in an active direction, right? So what we can see happening in this example of secondary active transport, okay, is that we have a sodium moving into the cell, right? So we know our electrochemical driving force for sodium is into the cell. So we calculated that out before. Baseline, okay? Or we might have just a concentration gradient for sodium listed, right? So we know that it happens to be high to low, because when we're thinking about sodium and how it acts on your typical cell, it what we'll think of as our resting condition. Both are chemical and electrical driving forces start out pointing in, right? So we could look at that chemical driving force as kind of a shorthand. Right, so this is our passive direction, our favorable direction. So if we only had sodium going in that direction, this would be active transport, right? That's the direction that should be passive. However, we see something different with glucose here, right? So in this situation, glucose, not an ion, so you don't have to worry about electrical forces on glucose. So we can definitely just pay attention to our concentrations. So glucose in this case is moving from an area where we have low concentration of glucose to an area of high concentration of glucose. So we're packing it in there, right? Trying to pack more and more glucose into the cell. You might imagine that like maybe we're trying to make a lot of ATP, right? So there's a reason to pull glucose into this cell, right? We want it for some reason. So this is the purpose of secondary active transport, is that we use something moving in the direction it wants to go, in this case the sodium, to pull something along with it, right? So in this case, we're pulling glucose in that same direction as the sodium, even though glucose doesn't actually want to go in that direction. So our source of energy here is that sodium gradient. And we set up the sodium gradient with the sodium potassium pump. This is a type of primary active transport, which is why this is secondary. So this has to happen after we set up that sodium gradient in the first place. So if we're thinking about the cellular process level, we use ATP to set up a gradient, primary active transport. Then we can use gradients to power the movement of other things as our secondary active transport. Yeah, so here we see that sodium linked glucose pump, we might refer to this, or sodium linked glucose transporter. You can see on the bottom it's labeled as co-transport. Co-transport means that sodium and glucose are traveling in the same direction. We don't always have this travel in the same direction if we're thinking about secondary active transport, although in this case we do, and we often see examples where we're going in the same direction. Okay? So we set up that sodium gradient with our sodium potassium pump, and now this sodium linked glucose pump is using that sodium gradient to pull glucose into our cell. So here's an example of counter transport. So this is when our two molecules, our two substances, two solids are moving in opposite directions. It's still an example of secondary active transport though. So as you're identifying this, one thing you're looking at is, I see two things moving. I should think about why that is. Well, let me identify the directions here. So in this case, you can tell because of the figure from our book that that green arrow with the sodium indicates that that's going in the direction sodium wants to go. So we can see that those hydrogen ions with their red arrow, hydrogen is going in a direction that's against its concentration gradient, or now we know, against its electrochemical driving force. Right, so sodium's moving in a good direction, hydrogen's moving in a bad direction, an unfavorable direction, the direction it doesn't want to go. So we know that this is secondary active transport. We have set up a gradient, in this case, again, a sodium gradient, that we can then use to power the movement of hydrogen. So this is a sodium linked proton pump. So we see our secondary active transport of hydrogen ions, which are really just loose protons hanging out in this example. So we're actively pumping these hydrogen ions, these protons, against their electrochemical driving force. And if they weren't ions, we would think of that as being against their concentration gradient. Since they are ions, they are charged. It's more correct to think of them as moving against the electrochemical driving force. So here we have a table of different types of transport. One way I sometimes like to study is by filling out blank tables. You wouldn't necessarily fill out this whole one, but you might select some information to help yourself go over all the types of active and passive transport, right? So here, this should probably go, we're going to add simple diffusion with our passive transport. Okay. So here we have those three types that we talked about. So we can see that we identify passive transport as going down electrochemical gradients in an unfavorable direction. Right, that's going to be our passive transport. And we could then fill in that our active transport is going against an electrochemical gradient, whether we are primary or secondary active. In both of these cases, we're fighting against that electrochemical driving force. We could then make sure that we know, do we need some type of protein to do this type of transport? So your book has broken out the 4 types over here separately and called them mediated transport. You don't need to use that term, but we have 4 types of transport that do require some type of protein. Okay? So we've got ion channels and carriers when we're thinking about the passive transport. We've got pumps when we're thinking about active transport. Okay? We can see that all our types of active transport required energy somewhere down the line. That's paired up with this fact that they need to fight this electrochemical gradient. But none of our types of passive transport need that source of energy because they're going in a direction that's favorable to them. So this table also summarizes what the source of this energy is for primary versus secondary active transport. Don't need it for passive, so there's nothing there. Here we've got a little bit of detail on those proteins. So this is pointing out that usually when we have a protein, those proteins can get saturated. Channels are kind of iffy situation. And when we have these proteins, they're going to be specific to a specific substance. So you'd say it's a sodium channel. You'd say it's a glucose carrier, not just a general channel, not just a general carrier. Right? So we can also see how that links up to what type of molecule is being transported with a couple common examples here. So you definitely want to be able to fill in something like, what are our directions we're looking for? Do we need transport proteins? Do we need energy? What type of energy is that? This other stuff is also kind of important to know, but I wouldn't focus as much on those if personally I were making a table. I think those are more be captured by our discussion of like rates of transport. So that's another way you can study and sort of practice figuring out how to piece together information. So when we think about what's happening in a cell altogether, we're going to have all these things happening, right? We don't have a cell that only does active transport. We don't have a cell that only does passive transport. We're going to have coordination between lots of different proteins on the surface of our cells working together to fuel these processes and use these processes. This is part of how we maintain our differences between our intracellular fluid inside the cell and our extracellular fluid outside the cell for the active transport part. And then we use those gradients that we set up, those differences that we set up with our primary active transport to allow movement of other things. So here we see the picture of what happens with sodium and potassium in general, right? So we can see our sodium potassium pump on the left-hand side. Okay, maybe I shouldn't say directions out, right? We see it over here, right? So we see this export of sodium creating an extracellular fluid that has high sodium concentration. And in general, depleting the inside of our cells of sodium. We can see that the reverse is happening with potassium, right? So this same pump sets up a situation where we have a relatively low potassium concentration outside the cell and a relatively high one inside. And then on the right-hand side, you can see what that means for passive transport if we open up a channel and allow sodium or potassium to move through a channel. That's going to affect the directions which these molecules move, right? So in this case, we see the passive direction for sodium through this channel is from that high concentration in the extracellular fluid to the lower concentration inside the cell. Sorry, for sodium, but if we were focusing on potassium, we'd be moving from the inside of the cell, the intracellular fluid with lots of potassium, to this area where we have lower potassium outside the cell. So both of these as drawn would be passive transport of sodium and potassium with those green arrows, and then our active transport, our primary active transport happening with that sodium potassium pump on the other side. So these things work together. So next, we're going to think a little bit about water. So we're going to be thinking about osmolarity and tonicity, because we're going to see that water behaves in its own specific ways that we can interpret. Okay. Cool. All right. So conceptually, if you track water as an individual molecule, it would work the same way, but we're going to have some caveats. So when we're thinking about water, we don't have water pumps in our bodies. So osmosis, the movement of water, happens in the passive direction, kind of by default. We mentioned the protein that our water goes through, the aquaporins. There are multiple types of aquaporins, but for now, just aquaporins. Okay. Now, water is a polar molecule, meaning it has little charges accumulating on the oxygen and hydrogen, but it's not charged. So it's not going to be affected by our membrane potentials. Remembering that the membrane potential is that difference in charges inside and outside the cell that we can measure in millivolts. So when I say the membrane potential of the cell is -70 millivolts, I mean there are a lot more anions inside the cell versus outside. Okay. But water doesn't care about that. Only our ions are going to be reacting to that membrane potential. So when we're thinking about water, we can just think about that. So conceptually, if we think about water, we can think about water moving down essentially a water gradient, right? So we can think about water moving from where you have lots of water, so like high water concentration, to lower water concentration. But this is usually not the way we actually talk about it when we're talking about it. Kind of a funny thing to measure water concentration. You probably haven't done that in any of your chemistry classes. Usually what we pay attention to when we're measuring what's in a fluid, we pay attention to solute concentrations, right? So when we're thinking about osmosis, we want to notice that here on the inside of the cell, right, where we've written low water concentration, right, and we actually gave it a number here, right, so this 55.2 versus a higher 55.5 outside, we can see that that low water concentration trades off with a high solute concentration, right? So low water and high solute mean the same thing for our purposes, right? And the reverse is true on the outside, right? So here we can see that where we have pure water, like 100% water, right? We don't have any solute, right? So this is an inverse relationship as well. And so where you have lots of water, you only have a little solute. Where you have lots of solute, you only have a little water. So this means when we're thinking about osmosis, we can pay attention to the water, in which case we can use the same rules that we just looked at for passive transport in our previous section of our transport packet. But often we're going to be thinking about how much solute is in this water and then kind of back solve. So in this other example, we can kind of apply that, right? So here we could see our water concentration listed at the bottom. Right, so here we have water concentration, 55.2, it's greater than 54.5, so water goes from the inside to the outside. But if we wanted to pay attention to just the solute concentration, we could. Okay. So we notice our solute concentration inside the cell is low. Solute concentration outside the cell is high. So the way I like to think about it is like water likes to move towards solute to water it down, right? Water wants to water stuff down. So in this case, the water is still flowing that way. So it's flowing towards this higher concentration of solute in order to try to get it lower, to try to get that solute concentration to match with the size of the cell. So you can figure out the direction water should be moving for osmosis if you're given the water concentration, but you can also figure out the direction water wants to go given just the solute concentration. Now, how do we think about the solute concentrations more mathematically? So when we think about the total solute concentration in a solution, it's going to be a little different than if you're thinking about like that solute in dry form on the table. So we're thinking about the fact that if you drop some salt into water, it takes up some of the space that the water was previously occupying. And with a little, you don't notice it, but if you dropped Himalayan salt lamps in your bathtub, you'd notice it took up some space. But our salts dissociate in water. So like sodium chloride is table salt. So it splits into 2 ion sodium chloride when you put it in water. So we have measurements that account for that. So when we're going from like our chemistry versions of measuring these substances, we're going to compare our moles, right? So 0.1 mole, something like glucose that doesn't dissociate in water, is just going to become 0.1 osmole in a liter of water. But if we're paying attention to something salt where we have ions separating, ionic bonds splitting apart, we're going to have to account for each of those pieces separately. So if you have 0.1 mole of sodium chloride, we're going to have to think about the effects that the sodium has on the water and the effects that the chloride separately has on the water. So in your mind, you're going to split that sodium and chloride apart. You're going to think, okay, I have 0.1 mole of sodium. I have 0.1 mole of chloride. So if we're thinking about how we would express the number of solutes that are floating around in our water, it's going to be double what we had when we were just measuring 0.1 mole somewhere else. So this is going to be important for the difference between the moles and the osmoles. Right, so we think about the osmoles when we're thinking about osmosis. So in this case, our sodium chloride had 0.1 moles of sodium chloride. But when we think about the effects on water, the osmolarity, we got 0.2. So these are our osmoles and how they relate to moles. Usually when we're thinking about physiology, our numbers aren't that big. We don't have concentrations that are quite so high. So usually you're going to see things measured in milliosmoles. That's what this MOSM is. And this is an 1,000. This is 1,000th of an osmol. So this is just small. This is useful because we have fewer solutes dissolved inside cells than we would be expressing in moles. So that's kind of extreme for your body. The usual osmolarity of our fluids generally, our ballpark comparison number is going to be around 300 milliosmoles. So when we're in equilibrium and water isn't frantically moving across your cells to try and balance stuff out, you're going to see that our intracellular fluid and our extracellular fluid may have different ions that are dissolved in there, but if we were to add everything up, we've got about 300 milliosmoles of like pull on water on each side. And I should say, we are thinking of these osmoles as basically measurements of a pull on water. So not directly a solute concentration, but that's essentially what it's measuring, is how much are these going to draw water towards themselves. Okay. So you may have discussed tonicity in the past. We can describe tonicity of substances and we can describe osmolarity of substances. There's a slight difference, but the phrasing is going to be similar. Okay. So when we're at a sort of equilibrium state, water isn't moving on net in any direction. You might have some moving in, you might have some moving out, but they'd equal each other out. We refer to this situation as isoosmotic, right? Okay, so iso is like same. So if we were at 300 milliosmoles, both inside and outside, right, that would be an isoosmotic situation. That would be an isoosmotic solution outside our cell. We can have differences in the solution outside compared to the inside. So in a hyperosmotic solution, what we're thinking of is something that has a high osmolarity outside. So hyper, then extra, right? So higher osmolarity, our number of osmoles would be greater in the extracellular fluid. And you can see in this situation, we have water moving out of our cell to try and water down that high concentration of solutes, leading to cells that potentially shrivel, get dehydrated. We describe them as crenated if we can see those little wrinkles that are forming as we get more dehydrated. In a hypoosmotic solution, hypo means low. So this is a case where like you have a cell in pure water, right? So no osmolarity at all, don't have any salts in there, no concentration, super low concentration of salts, of solutes. And in this case, since we do have some stuff in the cell, we do have ions and such in this cell, we're going to see water moving to the inside of the cell, trying to water down that concentration of solutes inside the cell. And this could potentially happen to the point that a cell bursts or lyses in a hypoosmotic solution. So because cells interact with their environment, interact with the solutions they're in, this is part of why it's important to know like what concentration is the fluid that you're giving someone, because this will have an actual effect on how their body is reacting. So we can also think of the concept, again, let's expand this, of osmotic pressure. Let's maybe spell smaller. Okay.
So osmotic pressure is something that reflects that total solute concentration. We're thinking about it as a pull on water, right? So when the word pressure is in this, we're thinking about, okay, our solutes are pulling on water. How hard would we have to work to stop that pull, right? Like how much pressure would we have to apply? How much force would we have to apply to equal out that pull? Okay. So we can see how that links up with our solute concentration and our water concentration here. Okay. So in this case, we have a solute concentration, let's call it glucose, so we don't have to do that doubling like we did with the sodium chloride. Solute concentration of 300 milliosmoles on side 1. Solute concentration of 500 milliosmoles on side 2. Right, so we can see that's lower on side 1, higher on side 2, which means that our water concentration is the reverse, right? More water on side 1, less water on side 2. So in total, our water wants to flow towards side 2, right? It wants to flow towards that area where we have less water and a lot more solute, right? So flowing towards this higher solute to water it down. And we can measure that with our osmotic pressure. Okay, so here we see our osmotic pressure. We've got a pressure unit, atmospheres on here. Right, so we can see if we think of higher as more pull, right, that osmotic pressure on the right-hand side, on side 2. Higher, it's pulling harder on water, so the water is getting pulled to that side. Now, if we wanted, we could even measure what is the difference between these two sides. What is the difference between the pull of each of these two sides? We might want to do that if we were thinking about like, how fast is this going to happen? What's the rate going to look like, right? We know that bigger differences, bigger concentration gradients have an effect on the rate that something diffuses, right? So a bigger difference in osmotic pressure is likewise going to involve water moving more quickly, more water moving. So when we think about tonicity, this is a related concept, but what we're focusing on specifically with tonicity is we're thinking about impermeant solutes. Okay, so impermeant solutes. That's the like extra specialization here, extra piece versus just osmolarity. Okay. So we're still thinking about a water gradient across a membrane. We're still thinking about solutes of different concentration inside and outside. But what we're specifying is that we're looking at solutes that themselves can't move, right? So we're not looking at like oxygen, which on its own can diffuse across a cell membrane, or carbon dioxide, which can diffuse across, or some small little fatty acid, which can diffuse across. Those might add into the osmolarity, probably more the lipids, right? You can imagine something that the membrane is permeable to. It might count as a solute, so might add to total osmolarity. But if it can cross the membrane on its own, then you're not going to need to move as much water as you would if we're looking just at the concentration of things that absolutely can't cross the membrane, right? So something like an ion in the absence of any channels. So that's what we're thinking about tonicity. Okay. So in this situation, we have an image where we're starting out with a situation where our solutions are isoosmotic, but they're not isotonic. So we're paying attention to this to kind of highlight the difference between the two terms, right? So isoosmotic means the same osmolarity on each side, right? So we can see in this situation that both inside and outside the cell, we've got an osmolarity of 300 milliosmoles, right? So that initial number is the same, right? So if we looked at just that and stopped thinking at this point, we might think that this isn't a situation where we have water movement. However, we are not in a situation where these are isotonic, right? So tonicity, we're paying attention specifically to impermeant solutes, right? So in this concentration, or sorry, in this tonicity, right, we're looking at a situation where we have lots of this impermeant solute inside our cell. We have basically none outside the cell, right? Okay. I'm gonna pause back a slide. Right, so in this situation, right, we are gonna see a shift in water, right, because of this high concentration inside the cell and low concentration outside, kind of like a hypotonic solution here. We're going to see water moving towards this impermeant solute at the same time as that yellow dot, that permeant solute that was initially adding to this osmolarity, moves on its own. Right, so in this situation, we can see that the urea here in yellow has its own concentration gradient, right? So we got chemical driving force on this yellow molecule. And it's something that the membrane is permeable to, it's permeant, so it can move into the cell on its own, right? So as it does that and comes to equilibrium on its own, right? This is now leading to a situation where we're raising that osmolarity inside the cell, right? So after our urea has moved down its gradient, we now have a situation where we have lots and lots of extra solute inside the cell compared to outside the cell, right? So now we start to see the water flowing along this new gradient that we're creating after we've given that first situation some time to settle. So this is why we care specifically about the tonicity, right? Because it's really these impermeant solutes that are long-term going to have an effect on water flow. Okay, so we will stop there. I'll get you guys a practice test up on Brightspace, and I'll post an announcement once that's up there. And I'll talk Friday a little bit more about this and a little bit about studying techniques as we're gearing up for our exam.